Let's do it. All right. So section 11.3 is all about partial derivatives. It's very big, huge thing. So partial derivatives, and what it's all about is the idea of we're going to keep one variable constant and take the derivative with respect to the other. Now, what do I mean? Well, if you think about it, it's exactly what we do every time you do an experiment. Okay? You're a fool if you change 14 variables at one time because you never know which variable caused the thing to happen, right? Number one. Number two, you may have changed 3 variables or whatever and ended up exactly where you are, and you're like, nothing changed. Well, that's because this one increased it, this one decreased it, perhaps. They worked against each other. You don't know. And so the idea is you keep one constant, you tweak with the other one. Now, I will never forget this. My kid says I should drop it. I can't. I'm sorry. I can't, Grady. I can't do it. When he was in 6th grade, everybody had to do a science fair project. His was great. He, 6th grade, 5th grade? 5th grade, maybe 6th grade. I don't recall. It doesn't really make any difference. One of those two. He said, I'd like to learn. I've heard about this thing called acid rain. I'd like to know more about it. Cool. So, get the pH meter from school. We have, I should have had Lee's litmus paper. And then I said, that's obviously not very different. So, you're going to we are calibrated testers. So, I said, all right, let's use these guys. So, his grandma and grandpa travel all around the Northwest that winter leading into spring. Other grandparents came down. Buddy of mine, came down and brought some water from rain from his area and so on. We had lots of samples from the beach, from all over the place. And he did a bunch of samples, and unsurprisingly, he didn't see a lot of acid rain in the Pacific Northwest. Geez, color me shocked. Anyways, there was very little variation between them. Okay, that was what he wanted to say, and he could have told you in 6th grade, idea about logarithms, about how, if it goes from a 6 to a 7, it's from a 7 to a 6, it's 10 times more acidic. He could have told you all that. It's pretty impressive. Whatever. He gets a friggin' red ribbon. I've still not heard the end of this from his mom. Wow. I'm like, I don't want to talk about it. Now, the guy who won, the kid that won, 6th grader, mind you, built all by himself, freaking hovercraft with the Briggs & Stratton engine, this huge helicopter blade basically underneath of it, and this whole pontoon of a thing. I'm like, uh-huh. Yeah, he made it all by himself, did he? Mm-hmm. Sure he did. Mm-hmm. And then there's another one where same thing. And then I was like, are you kidding me? Then this one blue ribbon one, the classic, the one I talk about the most, is the idea, look, I'm going to plant some, peas perhaps, I don't remember. The whole thing is they're planting some peas. Some are planted outdoors. Some are planted indoors. And then, of course, some got more water. Some got less water. And the idea is, if you want to compare the top row versus the bottom row, what you're finding the difference between is you're finding the difference between what impact water had on them. If you want to compare this column versus this column, you're going to compare what effect being inside or outside had an effect on them. That's exactly what we're doing when we talk about partial derivatives. Now, this term, for whatever reason, I'm going to do it a little different way than I normally do. Okay. Ordinarily, I do a little example deal first. I think I'm going to do it last this time because I feel like it, because I want to, because I'm going to. I don't care. So if you have z is equal to, and by the way, it's a function of x and y, so I could just easily written it this way. Is equal to, I don't know. We'll do a nice easy one here because I feel like it. Mr. Groom, you feel so generous today. Well, thank you. 3 cosine x, y. Oh, that's hot. All right, there you go. Cool. Plus 2. Sure. Nice. So we could write this a couple of ways. We could just say dz dx. Now, you notice I'm using the small deltas. Those are the lowercase deltas. That is indicative of partial derivatives instead of dz dx. Okay. We don't write it like that. When we do partials, we use this delta notation here. Okay, now that's cool. Another way to write that would be to say this way. Now, I don't know. I like them both, but, you know, whatever. I kind of dig this. It's kind of a modified Newton's approach. I kind of like it because once you get to second derivatives and stuff, I think this one's a lot easier to write. And so, whatever. I probably will write this way most of the time. However, when I get to chain rule, I do go jump back over to the Leibniz notation because I think it's easier to kind of see what it is we're talking about. So here it is. We're going to treat y as a constant. What's the derivative of 3x squared? Why, it's 6x, Jay. That's right. What's the derivative of this constant? 0. What's the derivative of this constant? Let me think. 0. Nice. Now, what is the derivative of 3 cosine x? Or minus 3 cosine x? Well, it's going to be plus 3, right? Sine of xy. Now, be careful. Remember, this xy looks an awful like just like, I don't know, well, for instance, something like 2x. If it was 2x, then what would happen? You would times it by 2 because that's the chain rule, right? Same thing is going to happen here. And then, of course, the derivative of 2 is simply, 0. Ta-da! Jay, can you do the partial with respect to y? By God, I can, sir. Boom. Again, one or the other. I will write them both for a few minutes. But one or the other, you look like an idiot writing them both. Whatever. It's like, I took a bath, and I'm going to go take a shower now. Huh? That's weird, man. One or the other. Okay? I'm not judging if you don't, but, whatever. Listen, if I'm holding x constant, then the derivative of 3x squared is nothing. It's a constant. It goes away. This becomes 10y plus 6. And then this guy here is going to look very similar. Oopsie daisy. You all saw that, didn't you? You all saw that and you all laughed at me. Remember I put, it's like 2xj. And then I wrote a 2 for God's sakes. It's y, you dummy. There you go. Let's try that again. Plus 3, now it's going to be x sine x, y. And of course the 2 still goes away. That's it, man. There's nothing to it. Wait, can my calculator help me with these? Yes, it certainly can. Am I going to be expected to know how to do it the old-fashioned way? Yes, you are. And yes, you need to be able to show what you're doing in that regard. Yes, indeedy. So, here's what's going to happen, yo. You are going to go on. You're going to say, let's take the derivative of 3x squared plus 5y squared plus 6y minus 3 cosine. Now be careful, you need to do x times y. If you do not, it will assume that xy is its own variable, and that will not be optimal. Comma x. So I take the derivative with respect to x. Boom. How about that? Now be careful, for whatever reason, it always puts the y behind the sign. I don't really get it, but we got the right answer. And then, of course, all one has to do is just change this x to a y. Boom, there's your partial with respect to y. Bam! I know what you're thinking. Jay, can we do second derivatives? In other words, can we do the second partial with respect to x? And the answer is, of course we can. Now, then the question simply remains, do you like writing it? I don't like writing it that way. I prefer this method. That's how I prefer. Hey, what's the derivative of this guy with respect to x? I don't know. I feel like it's 6. And I feel like this is a product rule, right? Kind of. Because you're like, oh, it's a product rule because it's 3y. Wait a minute. Y is a constant. So it's really the derivative of sine. What's the derivative of sine? It's cosine of xy. Now remember, y is the constant this time, so I need to times by y. Boom. In the calculator, you're simply going to come in here and go, comma 2. Oops. Well, okay. That would be the right answer, Jay, if you had done the second derivative with respect to y. There, that's the x one. Sorry about that. It was freaking me out a little bit. Now let's do the second partial of y with respect to y. So the second partial with respect to y is going to be 10. That goes away. Remember, x is a constant. So this is simply going to be 3x cosine of xy times the derivative of the inside with respect to y. So it's going to be just an x left over. And there you go. Piece of cake. Okay. In terms of how they are done, they are so pretty easy. Okay. Now you'll run into a few. Occasionally they're kind of disgusting. So we'll do a couple of those just for fun. We'll see if we can make a couple that are gross or something. Just for good times to see what you think about it. That's disturbing, but let's do it. Okay? Why not? I feel like, sure, let's do that. It's a little, I'm going to hung up on that today. Let's do that, sure. All right. So let's do with respect to x. The partial with respect to x would be then, oh, disgusting. Well, remember, this is really this. So it's the chain rule, so the derivative of the outside function leave the inside alone, times the derivative of the inside, which would be, with respect to x, would be 6xy, plus 2. And then with respect to x, those are constants, so nothing. And so your answer, I will write it thusly. The 2, and this garbage is in the basement, so I'm going to rewrite it in the basement down here. Bam. And then, of course, these guys all have a 2 in common, so I could just cancel this 2, make that a 3, make that a 1. We are home free, my friend. All right. Well, could you do it with respect to y? Probably. I'm pretty talented that way. I don't know. With respect to y, I believe, I don't believe, I know, the first part's exactly the same because it's inside of that outside function. So we must take the derivative of the outside function first. Times, now with respect to y, this is simply 3x squared because it's just like 5y or something. What's the derivative of 2x? Nothing, it goes away. Now here, be careful. This is a product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. Nice. That's gross. And so when it's all said and done, it should be 3x squared plus 3y squared sine y plus y cubed cosine y over 2 squirt bam, and I'm done. Okay? And let's see if we're correct. Let's see if the computer agrees with me. I had a weird teacher in junior high who was always, agree with me. It makes me feel good. You weirdo. I don't really care. If the computer disagrees with me, it might make me angry, but that's okay. Don't forget to hit times y. Nice. Okay, and now I got to close that parentheses because it's in the square root, and then I'm going to take the derivative with respect to x. And, oh, look at that. It's like I know what I'm talking about. How weird is that? Now, of course, this is one that doing it by the first derivative is not hard. The second derivative is a bear. I mean, seriously, do you really want to take the second derivative of that guy? I don't. So the ones I asked you to do second derivatives of, they won't be that bad. And, of course, you'll be able to use your calculator. You're like, that doesn't look quite like what we have. It does. They just factored the 3 out of the second part there. Okay. It is. That's good work, man. Nice. All right. Now you're like, what? That's cool. Can you show us another trick, Jay? Yeah, my God, I'd like to. Suppose you had this guy. I don't know. I feel like I haven't used 7 in a while. I'm going to go with 7. Ooh, that's fancy. Nice. That's awesome. No, I don't want to do that. That's gross. Don't do that. I was getting fancy, but then I realized that what I'm going to end up doing here in a minute, I don't really want to do something that gross with. Nice. So, of course, one of the first things we'll do, of course, is always, hey, we'll find the derivative with respect to x and with respect to y. So it's going to be 14x y cubed plus, yeah, there's an x in here, so it's going to be 1 over, remember the derivative of a natural log is 1 over what's on the inside, times the derivative of the inside. The derivative of 3x is 3, the derivative of y is 0, and so it's just going to put a 3 on the top. Okay, you could have put times 3, but I'm going to put it on top. And then, of course, nothing, not cute. Of course, I'm going to leave a little room, because I'm going to do the second derivative here, instead of the second partial here in a second. So let's do the first with respect to y. It's going to be 21x squared y squared plus 1 over 3x minus y. And then the derivative of the denominator with respect to y is minus 1, actually. Okay? Cool. Now, here comes the fun part. Well, that's not 100% the fun part. Let's do this. Let's go ahead and find the second partial with respect to x. Now, remember, this is really 3x minus y to the minus 1 power currently, right? So it's going to be minus 3x minus y to the minus 2 times the derivative of the inside with respect to x. So it's going to be 14y cubed. 3 times 3 is 9. And then this is going to be on the bottom squared. That should be right. I guess we'll find out in a minute. So with respect to y, it's going to be 42x squared y minus, and then you're like, all right, so let's do this. Remember, this is 3x minus y to the minus 1. Right now, it's a minus 1 times that. So you bring the negative 1 down, it's going to be plus 1. I didn't have to write that, but I did. Times the derivative with respect to y, which is negative 1. We should be good to go. Now, I guess let's check that just for a good time. We'll see if the calculator agrees with me. Oh, Mr. Calculator, do you agree with me? Well, you worthless hippie. What do you do? Oh, got 2 times in there. Yeah, look at that. I'm golden, baby. I'm golden. Let's go and do the second derivative whilst we're here. What do you know about that? I feel like that's what I have. Nice. And then, of course, come back in here and put that to a y. Boom, 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 boom. Be careful. Notice what it did. It flipped the negative, made it positive 1, and then flipped the bottom y minus 3x. Be careful. The computer is always doing that. Don't come crying to me because you think you messed it up. Just be patient and look at it again carefully. That's great. So we're correct. Now, there is another kind of derivative that we are going to look at. And, oh, for God's sakes. All right. And the second kind is this guy. And it's called the first mixed partial. It has a very useful purpose, and we're going to look at that in section 11.7 primarily. So what that says is that we're going to take the first derivative with respect to x, which was this guy, I think. Nope. No, it was plus. Wait, what? No, it was plus 3. And what we're going to do now to find, to write this guy, we're going to start off with this guy here. So to find this mixed partial, what you're going to do is you're going to take the derivative with respect to x first, and then whatever you get for that guy, you're going to take the derivative of that with respect to y. Okay? So let's do it, shall we? So if I take the derivative of this piece here with respect to y, I'm going to get 42 xy squared. And then, of course, this is really 3 3x minus y to the minus 2. I can't do that in my head. If you can, God bless you. You do it that way. It's going to be minus 6. 3x minus y to the minus 3 power times 3. So that means that what I'm going to end up with is 42xy squared minus 18 over 3x minus y to the third power. Kaboom. And you're like, hey, that was pretty cool, Jay. All right, yeah, but there's more. But wait, there's more. We will also do this. $21x squared y squared. And then we're going to take the derivative of that sucker with respect to x. And look what happens. You end up with 42x y squared. And of course, this is minus 1. This was to the negative 2, I think. That was squared, right? Correct. No. No, it wasn't. Sorry, no, it wasn't. It was to the first. Now it's going to be squared. Sorry. So this is really negative 1, 3x minus 1 to the minus 1. So it's going to become positive, right? Positive. And then it's going to be Oh, for crying out loud. I see 2 things wrong so far. Hang on. Okay, let's back the train up a little bit. Let's back it up a little bit. Let's do this first one right. Now, how did I know I was wrong? I'll tell you in a minute. I'll tell you how in a minute I knew I was wrong. And the reason I knew I was wrong was from the standpoint of what my answers were coming out to be. So let's just back it up here a little bit and just play along and have a good time. So when I do this fella here, let's do it again. Part of it was right, part of it was wrong. So here we go. It's going to be 42x y squared. Okay, that part was correct, I think. I think that's what I had. Anyway, plus, now here's where I screwed up. Okay, it was 3. Okay, but look, I'm going to bring this negative 2 down in front. Now, there was 2 things that were wrong with that. On the original function, it wasn't squared. It was just to the first power. So let's get that fixed. Okay, so that was part of my issue. And then I see there was another part of it here too. So what? Bring it down, it's going to become minus 3. 3x minus y to the minus 2 power. Now be careful, this is the second thing I messed up. It's the derivative of this with respect to y, so times negative 1 again. Now, this is why I love technology so much, because even though I'm tired, it doesn't care. It just knocks it out of the park for me. Could I do it by hand? Well, yeah, most of the time. Will I make mistakes? I don't know. Is the sky blue most days? Does it rain in Oregon like all the winter? Yes. And so on and so on and so on. Is the Pope Catholic? I don't know. And so on and so forth. So, yes, but I'd rather not, because I tend to make a lot of boo-boos, if you will. So let's try this again. And if this works right, you'll be like, oh my gosh, I see what it's supposed to be, Jay. So with respect to x, let's make it happen. 42xy squared. Remember, this is minus 1, 3x minus y to the minus 1 power. So I bring that down, it's going to become plus 1. 3x minus y to the minus 2. Doggone it. Y, that's a y, you dope. It's a y. And then times the derivative of the inside with respect to x, which is 3. There you go, stupid. What? Look at that. They're the same. And that is true, my friends. This partial is the same as this partial. Nice. That will always be true. A fellow by the name of Claro came up with that little tidbit of information. You're like, do I need to know that? You don't actually need to know that. In terms of who his name was. Personally, I just think it's kind of neat to know that it will always work out. That's a way a guy could have checked himself back in the old days. Now, this is the 21st century, for crying out loud. So if a guy's going to do this by himself in the 21st century, he simply goes back up here to see the There's my first derivative, right? You with me? Boom. That was with respect to x. So I simply throw a derivative with respect to y onto that guy, and lo and behold, that's what I got, dog. Now notice it flipped the denominator around, makes no difference because I'm going to square it anyways. Are you with me? Makes no difference. Why did I have no idea. I think they switch it around. They write the y's first because I took the derivative with respect to y. I think that's why they do it. Freaking programmers, you never know about those weirdos. Okay? They just do their own thing, man. And they're like, well, okay, cool, but why, Jay? Oh, glad you asked, friend. I'm glad you asked. Let's go take a look at this dude here. Just for a good time, shall we? And count plot 3D. You can just go away, you piece of garbage. I don't need you anymore. I don't need you in my life. You just leave me alone. All right, there we go. So it was 3x squared. Maybe if you push the button hard enough, you dope. 3x squared plus 2 times x times y, I think is what I had. Yep. Plus 4y squared. Kaboom. Oh, look at that. Oh, weird. OMG, gosh. What is going on? It looks like, oh my God, it looks, dude, look at that. From this side, it looks like parabolas. You can see them. Dude, from this side, it looks like, nuh-uh, it looks like parabolas. That's right. But why is that true? Let's talk about that for a minute. Now, you recall, the other day, we talked about in section 11.1, we talked about the traces, and we said let's let y be a constant, Jay. And we said that a trace then would have come down to be something like this. I don't know, something along those lines, because y is a constant, right? And so 2 times y is a different constant. But what does that look like? My God, it looks like parabolas. That's right. That's right. And then you're like, wait, but what about if I let y be a constant, or x be a constant rather? Then this would look like, I don't know, b plus 2ay or something to that effect. Well, you do you. Let's just call it ay plus 4y squared. My God, look at that. If this is z and this is y, it's parabolas. That's right. And so that's exactly what's going to happen. And we talked about that. But more importantly, check this out. How does z change as x changes? I don't know. 6x plus 2y plus 0. That's it. Like, what does that mean, Jay? Well, again, I actually like it in this formula better because I want to know how is it changing at a certain point. So when x is 2, let's say, and y is negative 1. So what this would be saying is I put that in as 12 minus 2 is 10. And so it'd be like, oh, what's happening? Well, z is increasing by 10 when x is 2 and y is negative 1. That's what we're saying. That's what we're saying. And what's happening? And x is increasing. Now remember, the whole point is that here, remember back in the day, we said what is the slope, or what is the derivative? It's the rate of change. So as x increases, what was happening to y? Well, that's exactly what we're doing now, except we're talking about what's happening to z as we increase x. Okay? And at this exact time, it's increasing by 10. Wait, what if it was at 3 negative 1, Jay? I don't know. Let's find out. Oops, fx 3 negative 1. I don't know. 18 minus 2 is 6. Oh, look at that. It's going up a lot faster. Well, it's a parabola, so I hope so. I hope so. We looked at it from that standpoint. We said it was 3x squared plus some x and plus some constant. Yeah, I hope so. I hope as you keep increasing, it's going to keep increasing. I wonder what happens in negative land. I wonder what would happen at x equals negative 2, 0 or something. I don't know. Let's find out. It'd be negative 12. Now, shut up. Because when we looked at it, we said it looked like parabolas coming down. Am I shocked that there might be negative slopes on this side? I'm not. I'm not. I'm really not shocked about this. So partial derivative is obviously going to give us a clue as to how x in this case is affecting z. Okay, and obviously it's going to change based on the values of x, and of course y will play a part in it as well. And so you have to be aware of that. Okay, that's going to be huge. And yeah, so then of course, what would the partial again of z with respect to y be? Or again, this way, I prefer this one. You do you. I'm not going to judge you. It's going to be 0, obviously. This is going to be 2x plus 8y. So what would this guy be at, let's say, 3 comma negative 3? I don't know. 6 minus 24 negative 18, I think. Sounds about right. And so you can look at it and go, yeah, that makes sense. All right, cool. Yeah, all right. Yeah. And so on, all the way down the line. Okay. Clearly, if we were in the first quadrant, if these had to be restricted to first quadrant numbers, so both positive, if you look at that, these guys will always be doing what? It's always going to be increasing, isn't it? Right? If the x's and the y's are both positive, it'll always be increasing in the first quadrant. Well, it has to. Because this is the change in z with respect to x, or in this case, in respect to y. And so as long as x and y are both positive in this case, well, yeah, it's going to continue to increase. Kind of a big deal. Okay? Now, in 11.4, we're going to do some more stuff with these guys, of course. That kind of goes without saying. But again, we're just going to practice doing them. Now, I feel like there was something else. Oh, and that mixed partial, you're like, that seemed kind of weird. Why are we doing that? Well, again, in 11.7, there's a very good use for that guy, and that's when it'll pop up. Partials will be used pretty much from now on throughout the rest of the book. You'll see them pop up. You're like, oh, there's a partial again. Wait, there's partials again. Whoa, partials. All right, partial. Partial derivatives. Okay, and in fact, this is, in essence, doing 251 over again. Okay, because that's what we didn't do. We start off with derivatives, and that's exactly what we're doing. We're starting off with these derivatives here and seeing where we're going with them. Okay, now, a couple other things to talk about. I don't mind if you practice using your calculator to check yourself at all. As a matter of fact, I highly encourage that. But practice doing by hand. I will have some on the test where you'll have to show me what you're doing by hand. So those will be not too terribly difficult, but you're going to have to do a little bit of, it's going to be pretty obvious that you know what you're doing. Otherwise, I'm not going to be really happy about that. Okay. Let's do one more, shall we? No, what? Yeah, it's equal to W. What? And that's typically what we do. When we add another variable, we say W is a function of X, Y, and Z. I don't know. I just work here. No one bothered to talk to Jay about it. I'm not real happy about it, but life goes on. Actually, I don't care. Not even a little bit. So let's talk about the partial of W, rather, with respect to X, you see. Let's do that. Well, with respect to X, this last piece goes away, so that's cute. This W is just going to stay there because it's, it's just a constant down in the basement. And so when I look at this guy, I think to myself, well, wait, can't I break this fraction into two pieces and write that as ZW? Z over W minus X squared over W? And the answer, of course, is yes, I can. And Z over W, there's no X's, so they go bye-bye. So there is your answer right there. Negative 2X over W. And while we're here, let's do the Y's. Now, for God's sakes, that's embarrassing. It's embarrassing. Oh, I'm going to just jump off a cliff right now. That's embarrassing. Oh, no! Listen. There you go. That's more better. You can't have W on both sides, you goober, Jay. You just fall off a turnip wagon? Idiot. All right. It's late. It's not really late. It's 7:22. It just feels late. All right. Now, with respect to Y, now this is going to be gross. So I'm going to start with the easy part first. With respect to Y, that's just 5Z because those guys are just constants. This piece here looks uglier than it is. It's not really that ugly. Okay, go with me on this. It's really Z minus X squared times Y to the minus 1. Am I right? And if you think about it, this is not a product rule. This is constants. Leave it alone. What's the derivative of y to the minus 1? Y, it's minus 1 y to the minus 2, right? So it's going to be minus, and I'm just going to put these dudes back on top where they go, right, over y squared, because it's y to the minus 2. And then let's try see if we can't not screw this one up too. That'd be kind of handy. Jeez, that's embarrassing. Yeah, put a W on both sides, moron. Good job. All right. Yeah, so this next one is going to be just, it's going to be 1 over y, I believe, yeah? Because, again, you can split these into two pieces, z over y. What's the derivative of z? It's 1, so 1 over y. And then what's the derivative of x squared? Well, with respect to y, with respect to z, it's 0. That's nice. And then, of course, this is going to be 5y. And, again, person can check themselves. Not terribly difficult. Not terribly difficult at all. Can I graph this function? No, I can't, because it's like 4 dimensions. Is this a legit function? Yeah, it's very legit. Well, I don't know if this is legit, but yes, it's very legit that you would have multiple things. Again, once you get past 3 dimensions, just go, hey, let's talk about where I have multiple variables affecting things in my life, and you know, like whether it's blood pressure, you know, whatever it happens to be, and looking at it from that standpoint, I think it makes it a lot better. And don't sit there and get all weirded out about. Don't get all weirded out about stuff. Now, this is what I normally lead off class with, and I find that the last couple of years when I've done it, people get kind of weirded out, and they lose track of what I'm talking about, which kind of annoys me, and I don't know why. I'm like, dude, you were right there. How did you screw this up? Well, then I don't understand what you're doing. And I'm like, well, okay. So listen, I'm going to bake some cookies. All right. Now, if you like me, and you like to bake a little bit, and it's kind of fun, whatever, all right, cool. You realize that the sweet spot is right around 12 minutes. You're like, Jay, no way. There's no way you're going to bake them for 8 minutes. Well, you could. Well, they'd just be warm dough. Well, I know, but I'm just saying. Now, what we're going to measure is our z, which is our, I'm just going to write goodness, actually. Goodness is a function of temperature and time. Jay, I'm going to cook my cookies at 250. Well, good luck with that, pal. I'm going to cook my cookies at 300. You're getting warmer. I'm going to cook mine at 350. It's more betterish. I'm going to do 400. I wouldn't. I'm going to do 450. No, good luck. And so I'm going to give these scores. And like 10. All right. 9. 8.7. These are goodness scores. How much would I want to eat this cookie? Notice that they drop precipitously. And there's no way that's a 6. No way. There's no way, Jay. This would be edible, but not really edible. This would be weird, like dried out, but not taste good. This would be, I don't know what that would be. Just gross, though. No, that would be disgusting. 12 minutes at 250. No way, Jose. I don't think this is going to be 8.7. Let's make this a little smaller. 10 minutes at 250. Gross. 0.5. I'd put 0. I'd put negative, but I don't think I can do that. That doesn't feel right. It's not going to be that good. How do I know? I've cooked a lot of cookies, man. And yes, I have fallen asleep while baking cookies and left them in for a lot longer than they should have. And yeah, stunk the house up. And yeah, not good. Not bueno. I don't know. There's some numbers. Whatever, friends. One can see that if one were to shade this, that this is the best. Yes? How did I get that? Well, I made it up. But I cooked a lot of cookies, and that'd be a pretty good time to start with. 350 for 12 minutes is it's a pretty good starting range. You should get a pretty good cookie out of that. Pretty tasty cookie out of it. So, excuse me. So, what I want to look at is this. As I change temperature, how is the goodness affected? Well, it kind of depends, Jay. Well, what do you mean? Well, if you were here at 12 minutes and 350 degrees and you increase the temperature, what's going to happen? Well, your goodness drops like a rock. It's negative. Are you with me? You are not improving, friend. Not improving. However, if you were talking about 10 minutes and 300 degrees, if you increase the temperature, what happens? Well, you'd be coming from this direction to this direction. You would be positive derivative, right? You'd be increasing in the goodness scale. And you're like, oh, yeah, I get that. And then you're like, well, okay, well, what about from here to here? What if you are at 10 minutes, 400 degrees, and you increase the time? You leave it in the oven for a little longer. So you're here and you increase the time. What's going to happen? Not good is what's going to happen. Not good. It drops like a rock. Okay? And so the idea here is what we can do is actually, if you want to approximate what is the rate of change, let's say, where do I want the rate of change to look at? Where do I want to do it? Yeah, right here. Let's look at this guy right here. Let's try to approximate this guy. So the rate of change, not 6.6, but the rate of change. Let's approximate the rate of change. And we're going to approximate it at 12 minutes, 300 degrees. Okay? Now, how would you do that? Well, I feel like, it seems to me like, anywho, that again, if we are, and you're like, well, what rate of change at that time? Well, by change of goodness, I should say, of goodness, by changing the time. Okay? And so what I want to do is I want to hold temperature constant. So I want to look across here. Okay? I want to look from here to here. I want to look from here to here, and I want to basically approximate them. So what I'm going to do is I'm going to go 10, 2.9. And I want to do 12, 6.6. And I want to do 14, 7.9. So what I'm going to do is I'm just going to basically find slopes. So 6.6 minus 2.9 is 3.7 over 2. And from here to here, it's going to be 1.3 over 2. Take a calculator out. What I can actually do is kind of look at that from this standpoint and just get you to see this. And of course, you could just average those guys. Now, you're like, couldn't I just add them and go from one to the other? You can in this case, yes. But that won't always be true. So what you're saying is this, is you'd be increasing the goodness by 125 goodness points per minute of change. Okay, that's what you'd be approximating. Okay, and again, all we did was we looked at it from that standpoint. Now, again, because these are the same distance apart, 12 to 14 and 10 to 12, we could have just gone from there to there. That won't always be true. You can have to kind of pay attention to what you're doing there in those guys. So just be aware of that. But probably the ones I give you. This is just kind of get you kind of getting the feel of what's going on. Okay. let's do this one here. Now let's approximate it at what about if I approximate the rate of change of goodness at 12,300 by changing temp instead. Oh, nice. So it's, instead of having 10, you see, I'm going to have 250, comma 2.9. I'm going to have, no, not 2.9, dope. 250, comma 2. You with me right here? So we're going this direction this time. 250, what did I say? 2.9? No, 2. I'm going to have 300, comma 6.6. And I'm going to have 350, comma 10. So if you define the slope here, that'd be a change of 4.6 over 50. And this would be a change of 3.4 over 50. So in other words, we're increasing about 0.08 goodness per degree of temp increase. Obviously, if it was negative, and if you're increasing the temperature any longer, increasing temperature, it would be dropping like a rock. Okay. Yeah, I think that's about it. The last thing I'm just going to kind of hint at, I don't think I'm going to actually do this example for you. I want you to kind of think about it. If a fella had a contour map like so, and we just drew one of these up relatively not too long ago here, and these were labeled, I don't know, 1, 2, 3, sure, 1, 2, 3. And let's just hypothetically say that you wanted to find and this is X and this is Y. You wanted to find, and remember, what are these curves here? These curves are the Z's. You with me? They are the Z's. And so let's say you wanted to approximate the change in the X direction at 2, 2. Well, here's 2, 2 right here. Okay. It's kind of a poor rendering, but here it is. What does this look like to you? This looks like 1.2. Oops, I forgot to tell you. These are 8, 10, 12, 14. Those are my topo lines. So this point right here would be something like 1 1/4, comma 10. All right. And then over here, you've got something like 2 3/4, comma 12. And you're like, well, what's going on in the middle there, Jay? Well, you could argue that right here, what have you got? You could argue that's 2, comma, you could argue that's, you could argue it's 11. I probably wouldn't get angry with you. And in essence, what you're going to be saying is like, all right, yeah, it's going to be 1 change in the height, right? A 1 change in height for 0.75 in the X direction. Nice, that's my slope. And for the other one, you're going to have, what are you going to have here? You're going to have, it's a 1 change over 0.75 again, handy. And because they're both they're both 0.75s, I'm not going to sweat it too much. I'm just going to go ahead and average them. So we're getting an increase in this direction of 1.33. Okay. If you're doing it the other way, to understand, you're going to have this amount here. You're going to have this amount here. This is obviously slower down here, higher up here. I'll let you finish that off. Reality, the only difference between this and the cookie one is that you have to look at the line and kind of approximate, guesstimate where you are in that situation. I'll let you finish that yourself. I think you should be okay.